I'm sorry again.
Okay.
My mistake. Thank you, Elena.
So I will continue. So we are in part of this interstellar medium that have some structure, and we simply would like to look into that. So what is neutral? How large part of this is neutral? So I put a table from a review by Friedrich et al. That is showing something that is known from the model. So these are not kind of observations, they are not the measurements, at least not directly measurements. So there are from some other type of measurements, what we can get from other measurements. And what you can see there are what is the number of the different elements in the interstellar medium, and what is the fraction of the non-ionized. So this is the first column that is pointed out with this arrow. And as you can see, what we mostly see as neutral is hydrogen, helium, oxygen, neon, slightly less, also nitrogen. So these are the most important chemical elements that we can expect as neutrals in the interstellar medium. And some of them, of course, can penetrate the heliosphere. And that's how we actually get most of the information about the local interstellar medium by probing this neutral inside. We will have chance with Interstellar to look outside. Okay, maybe we can go next slide. Okay, so how these neutrals are processed by our heliosphere. So I would separate two different effects. So one is the global interaction of our heliosphere that is changing the structure of neutrals in large scales. What we know most importantly for hydrogen is creating all the hydrogen wall and filtration of hydrogen. So not all of these neutrals can actually penetrate inside the heliosphere. So this is important. Of course, for charged particles, we don't see anything, of course, or maybe except for high energy cosmic rays. But for most of the charged particles, we don't see inside the heliosphere. But for neutrals, we see some part of them. So this is, of course, first filtrated in the outer boundaries of the heliosphere, but also it's modulated close to the sun by photoionization, charge exchange, collisions, electron impact ionization. Trajectories may be also modified by the radiation pressure. On the right, you can see how much we kind of lose as we are close to the sun compared to what we would see at the termination show. So you can see here that for hydrogen, we lose most of the atoms. So we don't mostly, it's very hard for us to directly measure direct sample hydrogen atoms. We have something, I will show the next slide, but it's much less. That is better for helium, oxygen, or neon, but still it's kind of processed. So it's not what's directly coming from the sun. We can go to the next slide. Okay, so here are some examples of observations that are made at 1 AU. So as I mentioned already, we have some direct sampling at 1 AU, and we actually were able to observe hydrogen, helium, or oxygen actually at 1 AU. However, as you can see, so here are these examples of these observations from Ibex's law. So it is possible to observe them directly, but except for helium that we have relatively high statistics and we can tell a lot about them. For other particles, this is much lower statistic, and it's kind of hard to get. There is also indirect ways. So for example, pickup ions observations, then we kind of can observe as we go around the sun, what's the change in the cutoff energy of pickup ions, or indirect also by backscatter Lyman alpha. This was earlier today, so I'm not going to rediscuss that. Okay, we can go to next slide. So other than, of course, the observations at 1 AU, we have some also observations beyond 1 AU. And here are some examples that we have from different spacecrafts. So one thing that we were able to observe indirectly as a result of the influence of interstellar neutral is, for example, slowdown of the solar wind. It was observed by Voyager 2. And so basically, because the charge exchange produce from the interstellar produce pickup ions inside the solar wind, this solar wind is slowed down, and as we are going away from the sun, and the speed of the solar wind is decreasing. So this can be observed, and this is indirect observation of hydrogen. There is, of course, also observation of backscattered Lyman alpha from Voyager, but also what and we have right now, it's from New Horizons observations of pickup ions. And this is actually the closest that we are able to direct observation, because we observe the products of these neutrons. And what we can see here in this figure, that so far we thought, for example, that its density is 0.09 after being filtered in the outer helioship, but now with this new value, it's 40% higher. So this is showing how important it is to not observe very close to the sun, where this is modulated by the solar wind, but going outside farther away from the sun. Okay, next one. So how we can use that for observation with the interstellar probe? This is an example what we should remember as looking into interstellar neutrons. So one important thing is that the spacecraft speed, in this case, will be comparable with the interstellar neutron atom speed. So we cannot neglect neither of these values. We cannot assume that the neutrons are at rest in the sun frame, or the spacecraft is at rest. So both these components need to be included. Actually, together, we will return to this later in André's presentation. So if you have about this energy or the angle we are looking, and this will be covered slightly later. But here I want to point out that regardless if we are going upwind, crosswind, or downwind, we should be able to see something interesting. Of course, the energy, as you can see on this panel, is different for upwind, crosswind, and downwind. So this is something that we should know upfront before making instrument design, as the kind of way how we observe may be slightly different. We may differently optimize our instrument. But what is also important, that we can observe different things and still will be something interesting. In the upwind, of course, we would probe directly hydrogen wall. And so this is kind of interesting, because we would be able to see this structure that's probably ahead of the heliosphere. Crosswind, on the other hand, this will be probably the easiest to see two separate populations that probably exist in the interstellar medium. And downwind, the signal would cover most of the sky. So it's not, because in this case, we are looking into difference of this relative speed. So this is the less favorable from the energetic point of view, but also the signal will cover most of the sky. So there is a lot of interesting structures, and also what is the structure in the downwind. We know that for some particles we expect that there is focusing cone in the downwind direction. Okay, next slide. Okay, so summing this up, I just want to say that there are two main things. So first, that we can observe with the neutral component, with the neutral atom detector of interstellar probe. First is the radial variation of the density. So we would be able not only to observe, to do observations not only inside the ionization cavity that we have right now, but also outside of the solar ionization cavity. And this would be important that we would do that with the same instrument. So also this is important, as I said, we see these big structures related to the global interaction. So we would be able to probe them directly, how this change, what is the fraction of atoms that can go inside the heliosphere. This is important, and this was kind of mentioned, I believe, on the previous meeting an hour ago, that knowledge of interstellar neutrons is important to interpret ENA observations, because ENA's observations are eventually a result of charge exchange between energetic protons and neutrons. So we need to know quite precisely what is the distribution of these neutrons inside the heliosphere to correctly interpret ENA observations. This is a very important part of this interpretation. But a separate thing is also the composition. So as I mentioned at the very beginning, there is a couple of chemical elements that become observed. And with that, we would be able to see these different elements, how they are filtered in these outer helioship boundaries, and also maybe for the first time observe some low abundance species that cannot make inside the heliosphere. For example, for carbon, there is only small fraction of neutral carbon in the interstellar medium, probably, so it will be quite challenging to observe even outside, but inside heliosphere we don't have any, so this is still quite important to understand what is with that. Okay, yeah, so that's all what I want to tell here, so André can probably continue with the rest of the presentation.
Thanks a lot, Pavel. I will continue. So this was basically introduction. So what's the science? What would we like to see? Let's continue with how to say, maybe a little bit, a few maybe rather technical slides, but what I sort of want to mention anyway, because how to embed our science, our discussions into the bigger picture, into the Sun Sensibility Matrix. So just to summarize, so far, according to the master Sun Traceability Matrix 11.1, what are actually the measurement objectives for neutrals observations, according to our present status? And here I just list mostly priority ones. Priority one, determine in situ the neutral gas temperature and density of H and other species beyond the heliopause. And actually this is mentioned twice in the Sun Traceability Matrix. So maybe we can just add it once, but on the other hand, it shows, because it's mentioned twice, that this is really very important. This is definitely a priority one. Then another priority one is directly measure and monitor the secondary neutral solar wind from a vantage point beyond the heliopause and compare to the plasma and neutral densities and temperatures. Again, it's this interplay between remote and in situ, between plasma and neutrals, and to compare with each other to get the full picture. Again, this sounds similar to what we had before, but it's still a little bit different, because another priority one is determine the plasma, well, that's not for us, but and neutral density and temperature of ISM species. So we already had before that we should determine the neutrals. Here we had determined in situ neutral gas temperature and density of H and other species beyond the heliopause. Here, this is even more general, but it's again, basically for us, it means determine the neutral density and the temperature. This is important when we talk about instrumentation for the different interstellar neutral species. And then this is actually, this is very important, and it's also very specific in terms of instrumentation. We are to measure the elemental and the isotopic abundances of significant species of the local interstellar medium, such as neon, oxygen, and some more species that are also listed in the Sun Sensibility Matrix. We will get back to that in a moment. And of course, it's mentioned, but we might in total put somewhat more emphasis on this, because this is really, how to say, there are some other priority ones here or measurements that are very important for interstellar probe, but some of this could in principle also be done partially by another spacecraft that doesn't go out 200 or 200 AUs. But when we talk about measure isotopic abundances and of the dominant species, but also of rather rare interstellar neutral species, this is really something that only the interstellar probe can do over the next 50 years. And here I said I only listed the priority ones. This is an exception. It's currently priority 2, but that's or no, now we're entering the discussion. We wonder if this shouldn't be a priority 1 as well, because when we talk about measuring interstellar neutrals, we must be aware that basically all the neutrals that we have measured so far, that we were able to measure at all in situ, so hydrogen, helium, there we already know that there are at least 2 components. There is the bulk flow that comes in from basically the upstream region, but then there's also a hot secondary population. This is the case for helium, for hydrogen, and we can assume, and probably for oxygen, we're also quite sure based on IBEX slow data, that also there are different species with different temperatures and different spatial distributions. So this is also very relevant if you want to talk about how are those neutrals, where do they come from, where do they originate, where are they produced in these interaction regions. If you just say, I just want to measure the pristine interstellar medium and know its chemical composition, this is of course very important. That's actually priority 1. But if you also want to learn about the interaction of your interstellar medium with your heliosphere and what happens in all the heliosheath and at the hydrogen wall, and you probably need to put a little bit more emphasis on also knowing those secondary components of hydrogen, helium, and oxygen. Currently, this is just a priority 2, but yeah, if we say that this probe really should teach us more about the interaction regions and the way the interstellar medium interacts with the heliosphere, then knowing and measuring those secondary populations that tell us about these interactions, it should be more important than it is now. So now going to the details of the Sun Sensibility Matrix, we added a lot of comments to the version 11.0. Some of those comments have already been incorporated. Some of them are still open, but they are written there and everybody can read our comments. So I won't go into detail about our comments to the general slides. That's the master STM. It's huge, as already mentioned several times before. Just briefly, some new thoughts or comments from our group that came up over the last 2 weeks that are not yet in here. Of course, the first thing is a general problem that you always have if you set up topical groups or subgroups to discuss such an STM. Some instruments are important to more than one topical group. So it's always the question, do you make groups according to science or according to instrumentation? Currently, our topical group is basically, well, it's about neutrals, but the way it is written in the Synergistically matrix and the way we have been working so far, we're also linked basically to a neutral mass spectrometer or to a given instrument. But of course, observing neutrals is, of course, there are several topical groups and several instruments that are relevant for observation of neutrals. We heard this, we heard the thing about the ENA low imager, which is of course relevant for ENAs, but is also relevant for interstellar neutrals. And of course, another classical thing is, of course, the UV observations. They are, well, it's about the UV spectrograph, but of course, there you also measure the interstellar neutral hydrogen. So we're not proposing yet that we should do it in another way, but we just have to be aware that there are those overlaps, but they cannot be avoided. And finally, one more question. There are 2 pale blue rows at the bottom of the master STM, so the current version, that don't really fit anymore into the matrix, but they are still there. So we don't know if they are obsolete or if they will be reincorporated. if you bear with me, I could even show what I mean. Interstellar probe. Let's see. I first have to look for it so that I know. Please bear with me. It's just here we go. All right. Do you see the Sun Sensibility Matrix on my screen?
Yeah, we can see it.
All right. Yeah, it's just here at the bottom on the master STM, there are those two pale blue rows that are related to interstellar neutrals, but they sort of, I think one of them is mentioned also above, but yeah, we're just not sure if those are obsolete now. But anyway. But we currently assume that that even if the rows aren't meant to be here anymore, the contents are very relevant, because here we're talking about measuring isotopic ratios of D over H and that stuff. Yeah, but all right, that's all I want to say about the master STM. Then, if I continue to the measurement requirements, we have the following here.
So we have a few questions in the chat at this point too.
Yeah,
André.
yeah. All right, please go ahead.
Sure. So Jay Wu asks, what does the secondary neutral solar wind mean? Secondary neutral solar wind.
Where did that come up?
Jay Wu, do you want to expand on that? Actually, I'm sorry. It looks like he's stepped off for the meeting. So the next question is from Viral. How can dust and neutrals be synergistically used?
Yeah. Ferle, do you want to say something more about your question, or?
I don't have an answer to the question because
all right.
But I think that it's kind of I just wanted to trigger some thoughts about I think the strength of this mission is that several groups and so on can do some synergistic work, and I just want to trigger this question, so if people can think about it, or perhaps in the social gathering have a beer together and
No, that's a very good point. It's again one of those maybe also overlaps between different topical groups, where sooner or later different topical groups have to get to work together and see what we can do together. Yeah,
but one question related: how big is the biggest particles that you can measure? So you only measure atoms, basically.
Yeah, actually, that's in the STM. Let me see if I find this. Here it is. Do you see now I'm on the measurement requirements key for the different instruments, and here for the dummy payload for the neutral mass spectrometer, we have their requirement elemental composition of lithium from hydrogen to iron. So it's really basically from mass from M over Z from 1 to 60 or something like this.
Okay. Yeah.
And there was another question in the chat, right?
Actually, Bob D. Magestri posed a response to Jay Wu, which is secondary solar wind is solar wind that has charge exchanged in the heliosphere. Basically the other side of the pickup ion.
All right. Thanks for answering for me.
Hello? Can you hear me?
Yes.
Hello, do you hear me?
Yes, you're a little bit mangled, but
Yeah. So I'm just wondering if the secondary solar wind means it's the neutral solar wind. Is those two things the same as thing?
Could you repeat? I couldn't quite hear your question. Maybe slow down a little bit.
So I'm just wondering if the secondary neutral solar wind is the same as just a neutral solar wind. Is it right?
Is it the same as the neutral solar wind?
As far as I understand, the neutral solar wind is really, well, it's just the solar wind lines that go away from the sun, and then as they travel outwards, they they are neutralized. So you basically have hydrogen ENAs that go radially away from the sun, which you could measure if you had an ENA measure that can measure actually ENAs while looking back towards the sun, which is of course an engineering problem. But I mean, that's the main component. And then, yeah, and then if you want the secondary solar wind, I think that this is also what Bob explained here in the chat is if you have solar wind, so you have protons that travel all the way to, well, they travel beyond the termination shock, enter the heliosheath, where everything gets hotter and slower, and there they do a charge exchange. But and then you have an ENA out there, which might travel backwards to the Earth, or okay, some more comments in the chat. Yeah, but yeah, I don't know if this answers your question. So, but here, I would say, when we're talking about measuring neutrals, I'm rather talk about the interstellar neutral, so hydrogen that comes from the interstellar medium towards the heliosphere. So hydrogen that didn't start out as solar wind protons, but rather as well, interstellar hydrogen traveling towards the sun.
Okay, thanks.
All right. Parisa, would you like to add something?
Yeah, I have a question. So
yeah.
What does neutral mass spectrometer can measure that ENA low can't?
All right, we get to that in a few minutes. That's one of our main discussions tonight or this afternoon. All right, so please let me just finish here with the Sun Sensibility Matrix. Assuming that we want to measure our interstellar neutrals with a neutral mass spectrometer. Assuming we want to use a neutral mass spectrometer for that, what kind of neutral mass spectrometer do we need? And you basically have the answers here in the Sensibility Matrix. That's so far so good. Here you have, how to say, the requirements that you want to be able to cover. Here you have the isotope ratios that you want to be able to measure, D over H, helium-3 to helium-4, and then of course also the carbon, oxygen, neon, and argon isotopes. If you get those isotopes for the local interstellar matter, you know a lot more about our neighborhood than you knew before. So all that's very important for cosmochemistry, and it's very important, well, to know the history basically of our part of the galaxy, and to relate those numbers to the solar composition. And then of course we added some more things. It's of course one key requirement is missing here. Sensitivity is very important. So how long do we have to integrate to get a useful measurement? And further on, we have an example heliophysics baseline. Still, if we assume that we have a neutral mass spectrometer to do our measurements, what kind of mass spectrometer do we need? This is basically a rehash from the previous slide. That's okay. Here, we added one comment about the field of view. We get back to this in a moment. And basically, we also revisited the mass and power and the technology readiness level that are already in here. And yeah, this looks more or less okay. Actually, for the mass, 5 kilogram should be enough based on available instrumentation. And regarding power, yeah, let's say 1,000 watt is for the power consumption. And the TLR, the technology readiness level that we have here, it depends a little bit on which you base your judgment on, but for many of the components, at least for this mass spectrometer, we basically have 7, which means things like this have already been built and have been flown or will be flown over the next few years. So that's not a big issue. And finally, if we want to have this planetary augmentation, so that we also can do flybys and measure funny stuff when you go near a Kuiper Belt object, of course, we have some additional requirements. The most important, if we go to our instrument here, basically the only addition we also, or requirement that we have to meet in addition, would be that our cadence must be fast enough. So we must be able to get useful mass spectrum within roughly 10 seconds if we do a flyby at an object. But again, this is that can easily be done. I mean, for the mass spectrometers that we're building for Mercury, for the icy moons of Jupiter, there 5 or 10 seconds is basically will be nominal operations when we do a flyby at Europa or Callisto. So that's not a showstopper. So let's return to the second part of the presentation. And I need to find out how. All right, I go back to the presentation. Hop, here we are. Yeah, so we saw this. And one last word about the STM, the mission success criteria. Pontus and other organizers asked me to say something about the mission success criteria. And you remember from yesterday, there's a threshold and the baseline. And of course, I briefly went through this a few days ago, and basically, I mean, it looks like a workable solution, but of course the threshold mission success criteria are really very modest. But of course, that's sort of probably the meaning, that's sort of the minimum that you need to fulfill that the mission is how to say, that it's worth to be launched in the first place. So that's really the very, that's really the minimum that you have to meet. And it's actually funny exercise. You can go through your dummy payload and then try to see, okay, how much do we need to carry to meet those threshold criteria? And it's actually quite easy. So for instance, you could easily fulfill your threshold mission criteria without any neutral mass spectrometer. For instance, just one ENA sensor, not 2 or 3, just one ENA sensor, EPS, PLS, and MAG. Or you can say, all right, I want a neutral mass spectrometer, one ENA sensor, an IDA, a MAG, and EPS. And then this combination is already enough to meet the yeah. I mean,
so I have a question for you on that front. When you say modest, and the way you just described it makes me wonder, is that good enough? Or are we setting the bar too low in such a way that the mission would be less than compelling? And do others have opinions about this same question? Because if we're setting the bar too low, then how a decadal survey panel would prioritize such a mission might not benefit us. If we're not pushing the limit, then why are we doing this? So I'd love to hear people's opinions on this.
Yeah, actually, me too. I just did this exercise a few days ago, basically myself. Personally, I think, of course, the threshold mission criteria must be modest, but I feel they are a little bit launch very simple mission with basically 1/3 or less than a half of the payload, and you're still basically good to go, which is, but that's my personal opinion. Maybe we could aim for a little bit a higher threshold, but maybe, yeah, any comments from the group here?
So this is Harakurik speaking. You know, if you tell me as a panel member that you can do everything with half of the payload, then I'm just telling you, look, then do it with half of the payload. You don't need that much money. You just go with that. And
that's a little bit the danger, yes.
That's the wrong way to go.
Yeah. Yeah. Yeah.
So I guess perhaps our challenge is to make sure that our baseline is being matched by what we're calling threshold mission success criteria. Yes?
Was that a question for me?
That could be a question for you, but
yeah, I'm sorry. We're about to start the Ascend webinar over here, which is giving us all kinds of troubles. But yeah, I'm glad you brought this up here. So in terms of the priority measurement objectives, one of the discussions and sort of is bouncing around in our minds, I think there is a solution where instead of talking about priority measurement objectives, you talk about just objectives, measurement objectives, and then you pick off, one or two of those. But it means for us that then we need to go through everything again and reorganize the measurement objectives so they become equally important, if you know what I mean. So that might be one of the outcomes that you're discussing here. I don't know. We should look into it. Was that the question, by the way?
So the comment or the observation is that to only answer 2 of the science questions under each science objective to get down to the threshold mission, we could basically toss out half the payload, half the measurements, and get there. And the corollary then is, why not make that your baseline and not ask for more money for more instruments?
No, the baseline is ideally the full science traceability matrix, right? And usually a threshold mission is set pretty low, and it allows us, as I said, also to sort of look at different scenarios should we come to that before the launch pad, right? And it's not just one threshold mission. And again, that threshold mission is
this is I made this exercise here listing 2 sets for a threshold mission criteria. So I think it's a useful exercise at this point, but it was just my sort of observation that it's that the threshold mission success criteria are really quite low. But that's maybe rather strategic than a scientific.
Well, I mean, it always comes back to us scientists, and ask yourself. If I only have these very few measurements out there, would the mission still be worth flying? Should NASA cancel the launch? And always our answer is, hell no, let's go anyway, right? Even if a very, very low threshold. And that's how you set the threshold. And under the question of should then the threshold be the baseline instead? Well, no, it shouldn't, because then you just reformulate the problem. And NASA always wants to see a threshold, right?
Yeah. No, I perfectly understand that there's a threshold in the baseline, and the threshold is even lower than a baseline. I understand this. It just might be that the current threshold is really so low that or as Harald pointed out, it might be dangerous, that it gives maybe the wrong ideas to some people that you can be much cheaper and still you should be okay doing your science. But that's a strategic question, a scientific question.
That's a legitimate comment. I mean, we should bring that up.
André and Pontus, can I have a comment here?
Yeah,
I had just been listening to this being away from the screen. With a mission like interstellar probe, there is a very important other consideration. Namely, it has to work for a long time. And then you might ask the question, what different scenarios you could come up with? And I was glad to hear that you have tried this for a minimum success criteria, so a threshold mission. You go in with the full payload, and then you ask the question, what is it that could potentially fail, and you still have your threshold mission intact, even if something fails on the way out, and you're getting the full board for a certain distance or a certain time. And I think with selling such a mission that ends up so expensive and yet is very daring, to have points to recede to even after it's launched and say, yeah, we made it. We can claim success honestly here. That's a very important consideration. Also for the funding agencies and for the community, I think.
Thank you, Eberhard. I actually have a similar question, or maybe a supporting question to this point. Is there a difference in the way that we should talk about threshold missions and minimum success criteria now as a part of input to a decadal versus how the program management and the NASA headquarters leadership talks about it later?
I think that's a very important point. That sounds good. Yeah.
This is Harold again. Sorry, I got cut off. But you know, we have to think strategically. The way, if we undersell the whole thing, maybe other groups, they don't do that. We probably kicked off the payload for whatever reason. And because they are not so shy and saying, oh, well, let's see, you know, what we can do. But if we sell it too modest, then I would say, sorry, so I got cut off again. So my question was, why, you know, if we sell it too modest, why we do it then at all? And you know, we have to think strategically, and also we have to push the envelope in some sense, because if we just talk about, you know, going up to oxygen, and so, well, IMAP has done it, IBEX has done it, so why you do it again? You have to push the envelope. You have to, you know, is this going to be a lot of, you know, years later?
Very good point. Thank you.
Yeah, I agree on that, Harold. It's always a very careful balance, not to sort of undersell it, because you're shooting yourself in the foot. Right?
Neither undersell nor oversell. Yeah.
So it's really important when we strike that balance for the threshold mission. So let us know if it is too low.
Yeah. That's just I didn't discuss it in full detail within our group, but personally I feel that it's let's say it's on the low side, the way we define the threshold or the minimum.
Let me just bring up the other aspect which is important here, is that, you know, showing that we have options is very important for a decadal survey. Because on the other extreme, there have been instances where, you know, the science community go in and they say, well, we have this, all or nothing, take it or leave it.
Going all in. Yes. Yeah. That's the other strategy.
In fact, for those of you who are familiar with the most recent space and solar physics decadal survey, that all or nothing attitude was applied to interstellar probe there, where it was either you have to start and go this fast or it's just not worth going at all. Basically said, without advanced propulsion, don't even bother.
Yeah.
Very good.
Yeah.
No, this is very good. I'll add this to my personal list. This will definitely be something we bring up on Friday, I think.
All right. I propose to go to the end or towards the end because it's getting late in the afternoon or in the evening probably. But that was basically that. So the last two things are number 5 is very brief, operations and data volume. And here we, Peter Coleman, collected inputs from the different topical groups, and we gave our input. And if you want to know more, yeah, you can look here at the spreadsheet. But basically, we found the following. Let's see. I briefly have to go to another surface. Here it is, yeah. Let me change to here. Yeah, it's again one of those matrices now for data volume. And here we have a good, how to say, we have experience of what we can promise and what not. If you go for a neutral mass spectrometer, then we know from PEP experience, so for on board the Jupiter Icy Moons Explorer, what it means. And there, basically, yeah, 1 bit per second means roughly 1 spectrum per day can be transmitted. I mean, 1 spectrum that meets all the criteria. So with going to masses of basically from 1 to 1,000 at the mass resolution that is high enough, and all that, including a little bit of housekeeping data. 1 bit per second basically means 1 spectrum per day. So that's not much. So, and if you consider Interstellar probe going out there for years and decades, we definitely can do something with this. And the good thing is, if we just want to reduce the data rate, well, just make it, I don't know, just integrate over a week and just send back 1 spectrum per week. So in this regard, mass spectrometry is sort of quite forgiving. You just have to reduce the temporal resolution. And with this, let's go to the last and biggest and the best point, the big science traits questions that are that have been opened up. So the 4 big science traits questions that we have identified and which we want to bring up here. When we talk about measuring interstellar neutrals, what kind of instrument do we talk about? In the dummy payload, you see a neutral mass spectrometer, which is fine for many of the questions, but not for all the questions. Basically, there are 2 options, 2 different types of instruments. We can think of a low energy ENA imager, or we can think of a neutral mass spectrometer, or of course, scientifically speaking, best would be both of them. Just a very brief example for those of you who are not familiar with what we're talking about. A quick example for a real life ENA low imager and a quick example for a real life neutral mass spectrometer. And all of this is already flying around in space. So it's out there, it's ready. A typical example, of course, for an ENA low imager would be IBEX low or IMAP low in a few years. Basically, what you do here is you measure energetic neutrals. They can be heliospheric ENAs, but of course they can also be interstellar neutrals, neutral hydrogen or oxygen or helium that comes into your field of view. Then you have to ionize your neutral and post-accelerate it, and then use the time of flight detector to detect a particle and get some information on it. We in Bern and some of our partner institutes have been working with those ENA imagers for decades. What do you get with such an ENA low imager? You get a modest energy resolution, but you get an energy resolution. So this is for IBEX low. You get maybe going from 10 electron volt to 1,000 electron volts, which is solar wind energy roughly. You get maybe 5 or 10 different channels. With this, you get a coarse energy spectrum. In terms of mass resolution, it's really very coarse. If I would say if everything goes according to plan, you can discriminate hydrogen from helium from anything heavier, but that's basically it. So you can tell hydrogen from helium, and you can tell helium from whatever heavier there is, but you have normally no chance to discriminate between carbon and oxygen and, well, and other stuff. So that's a little bit poor. The good thing, of course, about an imager is, well, you get full sky maps. In solar wind energies, you can observe hemispheric ENAs. You see your ribbon again, if you want to look at the ribbon. But of course, if you look around in 10, 20, or 30 eV, you see the interstellar neutrals coming in here. That's basically the sum of ISN helium and hydrogen, giving you this this map across the sky. So this is what you get with an ENA low imager. I would say a completely different type of measurement is a neutron mass spectrometer. This here is I would say, this image here shows a prototype. This was presented, I think, by Peter Wurtz 1 or 2 years ago in the first or second Interstellar Probe workshop. But the idea is basically you take a time of flight mass spectrometer, and then you can add, I would say, there are 2 different mechanisms how you can either directly measure the neutrals that come into your field of view here, and you can use an antechamber to accumulate your neutrals to get a better sensitivity, or you could even expose some aluminum foils for weeks or months, and then later heat up those and really measure the very rare species of your interstellar neutrals. But the basic thing here is, this is a mass spectrometer, so it means you have no energy resolution. You cannot tell, was this an interstellar neutral that came in with 20 eV or with 30 eV? You thermalize the stuff and then you measure it. So you don't have any energy resolution. And of course, you also only have limited spatial resolution, basically depending on where do you point your instrument at. But of course, you have high mass resolution. So instead of getting something like this, where you have basically 3 mass peaks and that's it, you get a real mass spectrum like this. And these are, both of these are lab data from prototypes or from flight spare instruments. So what does this mean? The good message first, neutron mass spectrometers that meet both the heliophysics and the planetary augmentation requirements as stated in STM 11.1 are ready to be built now. So that's really that's the most important thing. We are good to go in that respect. Second important thing is, if we have to decide between an ENA low imager and a mass spectrometer, this means basically good spatial resolution, moderate energy resolution, and poor mass resolution versus poor spatial resolution, low energy resolution, and high mass resolution. What does this mean for the Sun Sensibility Matrix? If we look at the requirements for interstellar neutrals, we see that, we should resolve spatial distribution and distribution functions of ISN hydrogen and helium. That's a priority 1. But on the other hand, we also have a priority 1 here. Elemental and isotopic abundances of significant species and isotopic ratios of D over H, 3 helium over 4 helium, and so on. If we take this at face value and we say we want to satisfy all first priorities, we need both instruments. If we want to satisfy all first priorities. Just as a side note here, if we also think about the planetary aspect, so if we talk about flybys, I'm getting to Pavel in maybe 10 seconds. If we talk about flybys, the ENA low emitter is not mandatory, but a mass spectrometer would be needed, basically with a 10 seconds cadence, which is okay. That's feasible. But now Pavel. Can you speak up?
Yes, so just a comment. So it's not obvious from the current version of the traceability matrix that we need both instruments. It kind of, I would say in some situations, it is kind of believed that with the neutral mass spectrometer, we are able to determine temperature. And this is not the case. For this, we need DNA law. But it's not noted in traceability matrix. I made some comments on that in 2 points where there is the kind of about temperature measurements that we need actually ENA law, not neutral mass spectrometer. So good point, but it's not noted actually right now in the traceability.
Yeah, or the way, yeah, that's correct. I mean, if you just list all the first priorities, then it implies that we need both instruments, but in some other respects of the STM or the way the ENA high, medium, and low is set up, it seems that sort of the ENA low imager, let's say, is sort of on the list of nice to haves, but not on the must haves. And of course, engineering wise and budget wise, I understand why it's a hard sell to have 3 different ENA imagers, but we just must understand what the scientific implications are for this. And yeah, it basically means, as Pavel already pointed out, that we cannot we get all this species and isotopic compositions, and this is definitely vital, but it means if we don't get the spatial distributions, which are also important to study those secondary components and to get a feeling of what is the temperature of those interstellar neutral populations that come into our heliosphere, which is relevant because it tells us something about the interaction and the way this interaction between the interstellar medium and our heliosphere actually works. And that's basically this first and probably the biggest science trade question.
Thank you. So we have about 10 minutes before the networking session on GatherTown begins. I put the link to it in the chat for everybody. It's also
great, thanks. Yeah.
And I encourage everybody to take these thoughts and more over to GatherTown and sign in. If you're going to use it, you should. It's recommended that you use Google Chrome. I believe some of the other browsers just don't work well with it. If that means you have to download and install Google Chrome, it only takes a minute or so to get that in place. I can stay here on this Zoom for a while. If anybody's having trouble with it, they can come back to me, or they could go right to the help session that Andrea Harmon has set up for people. This has been a great discussion, and André and company, congratulations on a great set of work here. The way that you've identified some weaknesses in the way that we've presented the science traceability matrix and the minimum threshold discussion was fantastic. That's exactly why we've invited all of you here today, so that we can learn where these things need to be strengthened. This was really great. Thank you, everybody.
Right. And now the last few slides are probably easy to digest, and some of this has already been, well, it has been addressed already at least twice today and also once yesterday. The second big science trade question is, of course, this spinner versus 3-axis stabilized spacecraft. And of course, here I echo what has been said, for instance, in the UV session, in the ENA session. If you just go for heliophysics science objectives, the spinning spacecraft is basically the way to go. And you can scan the spatial distribution of neutrals across the sky, and of course, it reduces spacecraft complexity. So here, just one question from our group. Again, that's again one of those discussion questions. We understand that if we want to do KBO flybys and stuff, we need a 3-axis stabilization. But the general question is, how important is it to include planetary science in the mission concept to make Interstellar probe a reality? We were wondering this because just based on the heliophysics baseline, if we say, yeah, it's a spinner is good enough and everything else just adds complexity. Yeah, we were just wondering, we don't have an answer here. But
so what we all missed, not being in the parallel planetary science section, covers a lot of that. And I know that Pontus and others will cover the fusion of all these things later on.
All right, great.
I can tell you that the planetary session, based on some other messages I've gotten over the last hour, imply a much more adventurous style, where maybe we add a second spacecraft to this that we kick off.
Oh yeah, I read a note about this.
But that's a lot of extra money and challenging. It's certainly in the trade space, though.
Yeah.
And actually, Kirby's put together a very interesting idea about doing a flyby on a spinner that we don't spin down. And it may be that there's a fused hybrid model of all this that makes a lot of sense.
Yeah. So this is hard again. I mean, that question, is it really important? Yes, it is, because, you know, if you have a long flight and you have nothing to report in the meantime, you know, you have a hard time to sell that thing. And if you have planetary flybys and you can say, I have seen this and this and this, makes a much better mission than anything, you know, you probably be able to see in 10 years, 20 years time.
Yes.
In fact, that sort of direction is 100% consistent with some of the earliest advice we got from our sponsors at NASA headquarters. That by creating a mission plan that had early milestones and interesting measurements and science return, not just 15 years out from launch, but along the way, would make this a compelling mission. And so that's why all these discussions are happening.
Just look at Voyager, you know.
Amen.
Yeah.
There you go. You have the answer.
Yeah, it's sort of, Interstellar Probe would be sort of an inverted Voyager, because we do heliophysics with also adding some planetary stuff, and the Voyager originally was basically planetary stuff, and now adding some heliophysics stuff.
You have to go out of your comfort zone in order to make this a success.
Yeah, good point.
Yes, indeed.
Yeah, but anyway, I think, but that's all I have to say here. So basically, from heliophysics point of view, we sort of, assume that it's a spinner, or at least that it can spin, so that we can cover the full sky. That's basically the thing here. And of course, related to question 1 and 2 is the field of view. Here, at least there are a few points that we can already make. The minimum requirement for a neutron mass spectrometer on any spacecraft anywhere. We must be far away from any outgassing to avoid contamination. The field of view must be completely unobstructed. And of course, the field of view must be large enough to cover the bulk flow direction of interstellar neutrals. And then, now talking about the spinning spacecraft again, axial mounting or off axis. If we assume that we don't go straight into the nose direction, which currently seems to be, so if you, for instance, assume this 45 degrees off the nose direction, then we probably would prefer a fixed but off axial pointing. It would reduce the exposition, as the atoms would enter the instrument only during a short part of the spinning period. But it would give the ability to observe the Mach cone angle and thus the temperature of different species. And of course, it would still mean that we can actually scan the sky.
A quick question about an assumption there. You said if it were on the spinning but off axis, then we would only see the ram direction occasionally. Is that what you said?
Yeah, the thing is, now this depends on the trajectory, and also, so there are still some, how to say,
you should assume that the spin axis and the trajectory are parallel, because the antenna has to point back towards the center of the solar system all the time on a spinning spacecraft.
Yeah. So, that's a good point. Pavel, do you remember what I think that was, we once had a discussion, and maybe I mangled something about the
I believe on the next slide or in the 2 slides, you have this figure that's showing.
All right, let's
angular distance from the pointing.
All right, let's continue here to the, and this is just this is just this discussion about the pivot platform. We heard that the pivot platform is in the, how to say, is a possibility for the ENA instruments. Of course, then we have a similar question here for the neutral mass spectrometer or ENA low or whatever. How about the pivot platform here? Of course, it adds complexity, but it should, we think it should remain in the trade space for now, because it would add flexibility in terms of trajectory and launch date and where do we need to be pointed during the mission. That's so it would add, I would say, freedom, but also complexity.
And how are you going to meet your mass budget? When I look at all this, I think I have heard you saying, you know, you have about 5 kilograms.
No, originally in Sun Sensibility Matrix, it was an estimate of 10 kilograms, and I just said 5 kilograms for the neutral mass spectrometer is enough. Of course, pivot platform, we're aware, of course, that's additional mass, and if we find out it cannot be done, then it cannot be done. It's just, we still,
I think, you know, we are talking about, you know, not just 5 kilograms, we are talking about 10 to 15 kilograms.
Yeah, then it's, well, it's off the table, but yeah, anyway.
Well, the point is, it's not really off the table. You have to come up with something, you know, I would say innovative. And, you know, I would not push it off just because I look at the mass, because things can made much lighter, and we have new technology.
Yeah,
so
all right.
Push it off the table. It's the wrong way to go. You know, you really have to get creative.
Yeah, anyway, so I said it's, how to say, if we can make ends meet and it works, and of course it would be great to have such a thing. But please let me just finish the last thing, choice of trajectory, and then we're done. Here, a lot of things have already been said, and we now assume 8 astronomical units per year, and we assume as a sort of a baseline this 30 to 45 degrees offset to nose, somewhere here. And of course, most important here, we can adapt to different trajectories. And just to make this statement, going close to the nose to study the hydrogen wall and benefit from relative speed, so going to 0 degrees here, would be great, but important message here, if we say, let's go to maybe 40, 45 degrees off the nose, so around here at the arrow, this would still mean that we lose, in terms of relative energy, that we have an energy loss of the incoming interstellar neutrons of roughly only 10%. Of course, it is felt, it's bad for statistics, but it's not a, let's say, disaster. So if we go 45 degrees off the nose direction, this still looks sort of feasible in terms of energy of the particles that we want to measure. And I think that's the, here, we have this thing again, and to resolve all those cross contingencies, you know, field of view, spinning, trajectory, we probably, the way we have to do this is first opt for a payload. So are we talking about a neutral mass spectrometer and or an ENA low, and then optimize the other things. And yeah, that's it. So if you have additional thoughts, either add them to the Google Doc now, or let Elena, who was so kind to take notes, know. And of course, don't forget the virtual networking session, which starts now, basically. Yeah, that's it from our side, from the topical group on neutrals.
Can we put the Google Doc link into the chat for everybody?
I think it was already put there. Let me check.
I can, yeah, André, if you could drop the Google link back in there.
Yeah, I dropped it at the very beginning, but it's, but for those, or Babe already put it there. Let's see, does this work? Yeah, and
very good.
There, of course, you can also have a look at the slides. They should be online, but you also see here on the Google Doc, you also see basically a summary of what I was talking about. And if you have any more comments, questions, please just drop them there. Yeah, that's the right link, yes.
And apparently there's some issue right now with the virtual chair GatherTown link.
Oh yeah.
André is resolving that. If people wanted to stay here and continue to discuss, you're more than welcome to. I will see if the other is up and running and let you know. But I'll stay here as well.
Yeah. All right.
And André just texted me that it's fixed, if you'd like to. And we're encouraging people to grab a beverage of their choice and a snack and make this as fun for yourselves as you can. But like I said, I'll hang out here for a few minutes if anybody has any questions about GatherTown or anything else, in fact.
All right. And with this, I'm going to stop my screen sharing and also stop the recording.
Thanks again, André. Great job.
Thanks for listening.
Thank you very much, André. It's very interesting.
I
learned a lot.
And thanks for collaborating on this. See ya.
So long. For fuck's sake, you know what? I just... What the hell did you do? I heard that we have to redock with a CubeSat somewhere at about 80 AU. Hey, Caitlin. Well, wait a minute. We gotta reset the dialogue here. We blame our women for so many things. I think this should be like the prodigal son spacecraft and not a daughter. The frenemy spacecraft. Oh, that's so that for the many years between launch and the encounter, it's getting power from the RTG. Oh, yeah. It could be right in the middle. But here's a trick though. If you were to have such a beast, it also would have to despin in order to not have the smear issues that we've been talking about in the first place. Are there enough? Are there enough dwarfs? Oh, am I yelling? Oh, I'm sorry. I'm going to turn my volume down. Right. So if we strategically say we're going to definitely get a dwarf planet, then does all this go away? Okay. he may be overstating the complexity of applying that to an instrument as well. Of applying that same stovepipe to an instrument. You can exactly, yes. Yep. Or the nose cam or whatever. Why not? But if Kirby, I'm really enamored of your solution of putting it on the RAM direction, a RAM cam. Get Planetary to pay for a RAM cam. Yes, there can be other solar system science or dust science or whatever that comes from it, but make it primarily a planetary instrument and make them pay for that. And then they don't even have to pay for fuel. So, but that's my preference. So this is my so who's used GatherTown before? Okay. I can't figure out how to jump. Vikas, hi. Oh, really? What button is that? Aha. Okay. Oh, now I can see you all better. Very cool. Oh, by the way, Caitlin, my wife said congratulations on getting the job at Goddard. When we saw you last year, you were still finishing up, so yeah. So, okay, so yeah, I think, I don't know. One of the things I've learned about interstellar space in the last few years is that because of the sparsity of the field strengths and the particle flows that are out there, that it's really hard to measure stuff with other things that we've built over the last 60 years as a race, as a species. And it's called Interstellar Probe, right? Not Voyager planetary mission. This is the Interstellar Probe. And so I wonder if we need to lean into it and say, first and foremost, we've got to make sure that our magnetometer and our wire booms can do that interstellar medium science as best as we possibly can, and then build out from there, which would make the nose cam the solution, right? That's my take on it. And that if we don't sell it first and foremost on the primary science that this can uniquely do, that we're going to be missing part of the point that I think NASA wants us to make, that the academies are going to key on. Catch you later, Alice. And hello, Yao. I don't know if you can hear us or not, because we can't see you at the moment. I need to go get mine actually. I'm gonna wander a little bit and see who else is here because I think there are. Let's see. There's about 20 people in here actually. Who else? And I don't know a couple of them. This is interesting. Yeah. Wait, really? Cool. I'm gonna try that. I'm gonna try that. But keep this going, and we're gonna definitely talk more about Prodigal Sun spacecraft and all kinds of stuff. All right. Check you later. I'll be back though. Hello, can you hear me, Jonathan? Hi. Not at all. What's up? She can't get in here or she can't get into Zoom? Oh, okay. Gotcha. That's A-okay. I'm just trying to learn how to use this better, so. I am, yes. I just tried to talk to Jonathan, and he wasn't there. His icon's there, but he wasn't talking, so. I'm gonna go grab a drink actually, in the spirit of things. All right, you go ahead and help her. All righty. All righty. Hello. How are you doing? Very good. What do you think of this this tool here? Yeah, it's I feel like I should be jumping over barrels or something. But it's pretty cool. Yeah. I can't remember where are you from exactly? Florida. Okay. Florida Tech. Welcome. I'm so glad you could join us. Very cool. What are you studying? Very good. Very, very good. Yeah, this is a neat tool. There's a whole knot of folks from APL talking about what just happened in the planetary section upstairs. If you want to go listen to an interesting conversation, have you figured out how to use the follow function yet? So on the right, there's a little white arrow on the right-hand side of the screen. If you click that, you'll see a whole list of the participants. And if you click on Kirby, for example, where's Kirby? You click on Kirby, it'll pop up a window and it says locate. you follow the yellow line that it creates, and it'll take you to Kirby. It's an animated bunch. But our teams have used this before. I haven't used it myself, and I'm going to wander around a little bit. And it's nice to meet you. I'm glad you've been able to join in. All righty. Catch you later.
Andrea Harmon.
What's that?
I see Andrea Harmon's name. Oh, your camera's on.
Here, so let's find Kirby. Okay, Kirby. Do.
I like your hair.
Yeah. So these are the posters.
Ah.
And you can look at the posters. Oh, but you can't walk through them apparently, because that's important. Mm-hmm. Then you go back upstairs, and you can sit down at a table and talk with somebody, or hang on, you can walk into a conversation.
That's tomorrow. I mean, you can go look at the posters now. Okay. Over here. It's because we're talking about spacecraft.
Amazing.
Michael, welcome back.
Welcome back. Hi.
You're muted though.
Oh, am I?
Nope. There you go.
No.
Actually, I have an open question for everyone. What are some engineering challenges that aren't being looked at by anyone?
That's so cool.
Navigation right now is still kind of up in the air. We have been assuming it's going to be a lot like New Horizons, but no one's really reading the numbers. So one thing. So my question for you, Wayne, is with the nose cam, where you're constantly staring at a dwarf planet that's ahead of you forever before from Jupiter onward, does that help with OpNav? Yes, but once you pass your planet, you don't really have, what do you have now? In Kirby, you're not looking at the dwarf planet. You're actually
And do you, so Wayne, you said navigation's a challenge, but is it simply really hard to pin down that flyby and then the rest of it's a breeze, or is there more navigation to worry about than that? So wait, so there's a maximum distance that'll work on because of the resolution of the size of the Earth, right? Huh. That's Doppler one-way ranging. Yeah, you put the transceiver on board in a certain mode, and then you basically ping it with you put all of your transmit power into the ranging tone, or as much as you can into the ranging tone, and you do it like Gabe said with two stations simultaneously, and you basically do some triangulation on the spacecraft. I don't understand all that RF magic though. Hello. How you doing? I'm doing well, thanks. Good. Yes. Yeah. It was fun listening to the neutrals session as well. Yeah. It's so important, I think, for us to be uncomfortable now, because that'll help us not be uncomfortable later. Yeah, and André, the way André kind of tackled some of those issues was great. Yeah, the whole lot of them. Yeah, so I'm wandering around this really cool tool looking for people that I don't know to say hello to them. So, but all right, cool. I'll catch you later. Yeah, you too. Bye. Hello, Robert. Hi, Abby. Oh. Hello. Good. You are in the basement where the posters are. There's a little white arrow on the right-hand side. If you click on the little white arrow, it'll pop out a whole list of everybody who's here. So if you like click on Caitlin, for example, you can locate Caitlin. And then if you locate Caitlin, it'll pop up a yellow line that'll allow you to follow the yellow line to go find whoever you want to talk to. So yeah. Yeah, I'm still here. Yeah. Yeah, no, it's that's in your clean poster space. Yes, your virtual poster space. How have you been? It's so good to see you. Oh my goodness. Wow. Yeah, Stefan walked past us and must have come and gone. Didn't stay for any conversation. He just disappeared. Oh no. Yeah, I don't know. Okay, yeah, no, I don't know who she is. Yeah. Yeah, how was the discussion? I was in the neutrals this afternoon. How was the planetary discussion?